Today was a snowy day. Felicia decided to track the snowfall. There were already 2 inches of snow, so we're going to highlight that part. Felicia measured the snow from today's storm. At the end of each hour, she found that exactly 1.5 inches of snow fell each hour. If it snowed at the day's rate for 5 hours, so only for 5 hours, how much snow was on the ground at the end? At the end of the problem, what we're trying to find out is how much snow was on the ground at the end of each hour. So now let's pay attention to our table. So they told you that there are already 2 inches of snow at the beginning. So at 0 hours, technically there was already 2 inches of snow from the previous storm. Now they're telling you that it's going to keep increasing by 1.5. So that means that after 1 hour, you're actually going to get you're going to have 3.5 inches of snow. And then you're going to have 5 inches of snow. Then you're going to get 6.5. And then you're going to get 8. And then 9.5. And that's just adding 1.5. In the table, 0 represents the time when the storm started. How much snow was on the ground then? We're going to write 2 inches. Then how much snow fell in the first hour? We know that every single hour you're only getting 1.5. Technically, there are 3.5 inches of snow at that time, but only 1.5 fell. Everything else was from something that was already there. And then it says, so how much snow was on the ground when Felicia measured it at the end of the first hour? So we know that there was 3.5 because you have the 2 initial plus the 1.5 of the hour, and that gives you 3.5. Not rocket science. Then it says, describe how you can use addition to find the depth of the snow at the end of each hour. We already did that in part C. We just put initial two inches plus 1.5, which is your rate. And then it says, suppose you multiply each hour in the table by the rate of 1.5 inches per hour. What else do you have to do to find the total depth of the snow? We already know that after 5 hours, you're at 9.5. So if you multiply 5 hours times 1.5, that's going to give you 7.5, and then we need to add the 2 inches, and that gives you 9.5. And then to write an equation for this situation, they already tell you which variables to use. They say let S represent the depth of the snow in inches and H represent the hours. So we're actually trying to find out how much snow we have. So that's going to be S for snow is equal to our rate, which is 1.5 hours plus 2. Now it says you're familiar with proportional relationships that start at 0, 0. For example, 0 hours worked means $0 earned. The problem on the previous page does not include 0, 0 The problem says that there were already 2 inches of snow on the ground at hour 0. This function starts at 02, so the initial value or the starting output value is 2. Okay, so let's highlight that part. Our initial value, or pay attention right here, is also the starting output. But realistically, we're never going to be using those terms. Maybe initial value here and there, but the proper term that we want to memorize is y-intercept. This quarter, and for the next 3 years, you guys are going to be dealing with linear functions. And it can be a little challenging to understand linear functions and try to make sense of an initial value. Why? Because whenever you're looking at a line, in this case, you actually have a starting point. You can actually look at the line at the point right here, and you can find your initial point. But most of the lines that you're going to be working with, they're going to be from negative infinity to positive infinity. So they're never going to start, they're never going to end. So using the initial value is going to be challenging because in negative infinity, you're never going to find a point. So what we're going to be paying attention, or starting point, is going to be on the y-axis. You're going to look in where the line touches the y-axis. And that's going to be your initial value or your y-intercept. With the initial value, we're also going to need a few other things. The other thing that we're going to need in this case is going to be our rate of change. So it says that x values and the y values change at different rates, but the ratio of these changes is always the same. Okay, so let's highlight that part. We have the x values and y values change at different rates, but they're always the same. The ratio is always the same. From point to point, the y values change by 1.5 units and the y values change by 1 unit. So the rate of change is 1.5 over 1, or 1.5. And we're actually going to use a different word for rate of change as well. We're going to add the word slope. We're going to get into a lot more detail in lesson 8 and lesson 9 on slope, but it makes a lot more sense to introduce it right now so you have an idea of how to work with slope and do the basic things with it. So the slope is going to be what we call delta y over delta x. Okay? Your slope is going to be delta y over delta x. Now, delta is a Greek letter that in math and in physics we use it as change. It means a change in your y values compared to your change in your x values. If you look at different programs, different videos, you're going to see that some people call it rise over run. Now, this means how much is it going up or down and how much is it moving to the right, left or right. Now, I personally like to read things from left to right like any other normal person, right? So I'm going to be reading my graphs from left to right. So technically my x is always going to be increasing, but my y is the one that is going to be either increasing or decreasing. Now, other people like to read it from bottom to top, but for me that's a little too weird. So I'm going to stick to reading it from left to right. From left to right, is it going up or is it going down? Okay, now our slope formula is going to be y2 minus y1 divided by x2 minus x1. And like a recipe, if you follow this formula, you're never going to go wrong with what you're trying to make. In this case, we're trying to get the slope. Now, to find the slope, this is what I'm going to require from you. I need you to actually draw boxes. And it will be a nice visual aid to understand what are we going to plug it in and when are we going to do it. So I want to actually put in right here y2, y1, x2, x1. So the first one is going to be y2. My y2 can be any point on the graph. Okay, so we need to choose 2 points to figure out that part. So I'm going to choose this point right here, just because I see that it crosses 2 integers. So that point is going to be 3, 8. And my first point, the wisest thing to do is to use the intercept right here, and that's going to be the point 0, 2. So this is going to be my x1, this is going to be my y1, and then the point that is going to be on the right is going to be your x2 and your y2. So we're going to plug in the numbers, and again, your y2 is right here. That's going to be 8. So we're going to put 8 minus, now you're looking at your y1. In this case, is going to be 2. So we're going to put 2. And then we're going to get 4 minus 0. 8 minus 2 is going to be 6. And 4 minus 0 is going to be 4. So your slope in this case is going to be 3/2, which is equal to 1.5. The other option is you look through the point and then you go up, you count, and then you move to the right. And that's how you can also do it. The only issue with those cases is that not every single point is going to be precise, and some of the numbers are going to be in between, and you don't know if it's 0.3 or if that's going to be 0.5, which is complicated. All right, number 1 says Dora opened a savings account and deposited $50. So let's highlight that part. Okay, a deposit, it's a positive number, so let's make a note of that. That's going to be plus 50. Then it says, when she gets her paycheck each week, Dora will put 25 into the savings account. It says, describe the initial value and the rate of change for this situation. So your initial value the money that she started with is $50. And your rate of change is going to be how much she's putting on a regular basis. And right here, they're telling you that it's going to be each week. Whenever they mention each or every or per, that's an idea of a rate of change. So you're going to be your rate of change or your slope $25. This is one of those problems that I'm telling you that it's pretty annoying to try to use the rice over run and try to count, because you won't be able to clearly see exactly where your points of intercept are. So whenever you're dealing with the maple tree and you need to choose 2 points, the point right here, it looks like it's half, but right here it looks like it's 0.75. So this is going to be I'm sorry, this is supposed to be somewhere around 3 because it's going to be in between here, but then this is supposed to be like 3.5, and right here somewhere this should be 4, but it's not clear. I usually prefer using those numbers right here. So for example, this is 2 and 4. You can clearly see the lines where they intercept, but that is the only one because everything else is somewhere in the middle. So using rise over run there is not usually effective. The problem says a biologist studied the growth of 2 different trees over a 5-year period. So I feel the 5-year period should be something that we should pay attention to. At the beginning of the study, she measured each tree's diameter. Okay, the biologist took the same measurement each year to determine the growth. The red maple in her study has a starting diameter of 4 inches. The diameter grew at an average rate of 0.3 inches per year. So let's highlight that part. And I'm actually going to write it down. So we know that the red one, your initial value is going to be 4, and your slope or your rate of change is going to be 0.3. And then it says the graph on the right shows the growth of the silver maple tree. Which function has a greater rate of change? So now we're looking for the silver one. And for the silver one, we know that the initial value is somewhere here, and that's going to be, it looks like 3. So let's write that down. So the initial value is going to be 3. And now we're looking for the slope. To find the slope, we're going to choose 2 points. The first point, this looks like that's 0.3. So let's put that down. And then we're going to look for another point. Now this point right here, it's between, so I'm not really happy with that, so I'm going to jump one more. This is going to be 2 and 4. So I'm going to use the point 2, 4. And using the information from the previous page, we're going to label this. This is going to be your x1, y1. This is going to be your x2, y2. And now the only thing we need to do is plug it into our formula. Now we don't have a lot of space there, so I'm actually going to drop a little and do it in the blank space right here. So rewriting our points, we know we said it was 0.3, and then we also have 2.4. And we're going to label them one more time. Right? You guys need to draw your boxes because, again, I don't want to see the mistakes when you mix your x's and your y's. And then we're going to label them on top. This is one of those formulas that you need to know by heart. You can hate it, but it needs to come from the heart. All right, so y2 is going to be 4. y1 is 3. Again, and those numbers are just coming. y2 is right here. That's our number 4, and I put it right here. And then you have y1, which is right here, and the number is 3, so I'm just writing it down here. The next part is x2, which is 2, and x1, which is 0. Four minus 3 is going to give you 1. 2 minus 0 is going to give you 2. Now, in the other problem, we know that the rate is 0.3, which is a decimal, and right now we have a fraction. It makes no sense comparing decimals and fractions. So let's try to put it into a decimal form. So I'm going to put it as 0.5. So we can can go back up and we can actually change the slope, and we can actually say, I want to cross it out. We can actually cross it out, and I'm going to put 0.5. That is the slope for the silver tree.